Hello everyone, this is Universum, a place where you learn about the entire universe, how it began and how it will end, and things that are similar to that. So what I'm about to tell you is how the universe began. This kind of matched the first episode due to it being the absolute first episode of this entire series. So now, everyone thinks that it all ought to start with a bang, instantaneously, out of existence. We don't know how that happened. If you look into quantum theory a little bit longer, you'll find out how, well, at least we think it began. We don't really know how exactly it began. I think that the Big Bang is an irrelevant term. I think that it should be called the Big Inflation instead, due to the way quantum behavior works. So, in the early universe, there were two particles. And a particle of superposition that was any particle you can think of. A tau antineutrino, a positron, a proton, an electron, any of those two. One positive charged and one negative charged particle in the universe. They'll come toward each other and then annihilate one another due to opposites attracting one another, and one of Newton's laws. For every action there is an opposite and equal reaction. This applies for everything in the universe, including particles. So now we must dive a little bit deeper into the quantum behavior. Although first, we need to understand one principle. The Heisenberg uncertainty principle, if you will. The Heisenberg uncertainty principle basically is, so you can measure the trajectory path of the geodesic that is in front of everything, so you will. First, we need to understand what a geodesic is. So now there's two types of geodesics. There's a geodesic which is just a line segment which can connect to other line segments, which can connect to other line segments, and create ion bonds and shapes alike. One other type of geodesic would be what is in front of you, what is moving you, what is moving all the particles that are inside your bodies all alike. Those are all geodesics. The line segment that keeps the universe in motion. So now, we must learn about, but in order to understand what the Heisenberg uncertainty principle is, we understand that there always going to be some uncertainty in how particles move in certain ways as possible. Since you can try to measure the trajectory path of a particle as much as you can. There may be a retrograde path, there may be an ellipse, who knows. But there always will be one uncertainty principle. One little piece of uncertainty. There may be some sort of massive object that may come in the way of it, out of nowhere. Well, really, there's no such thing as nowhere. There's always something. There always is such thing as somewhere. There's no such thing as nothing when you think about it. There always is empty space. It's changing and irreversible. If you get rid of space, you get more space. Get rid of that space, you get more space. It's a controversial law of the universe that you can't get rid of. So now, we have a little bit of understanding of the Heisenberg uncertainty principle. Basically, it's the way particles move, the way they behave, and the reason why we'll never be able to understand why particles will move in certain directions, due to the ways of quantum behavior, the fluctuations of particles around it, and even changing of the Higgs field, and of the mass of the particles and the potential energy of them, which may create a false vacuum, eventually leading into vacuum decay, and creating all sorts of messes, including changing chemistry itself, due to the universe changing, and its laws will become different. The new Higgs field will demand new and more stable particles. So everything in the universe will just obey these new laws of physics. Isn't that life itself may not even become possible anymore, due to this horrible thing that may happen. The vacuum decay may be a scary fiction, or maybe a controversial law of the universe. As far as we can tell, it's like measuring a continent, as some scientists say. So now that we've moved past the big inflation and how two particles colliding with one another can create strong outward force energy pushing against the Higgs field and pushing energy out, creating the expanding universe and dark energy. We'll get to dark energy a little bit later in this video. So then after the Big Bang, then there was these sort of superparticles that were created from these particles. They are called quarks and gluons. Well, actually, before them, there are these particles that are called preons that are inside of the quarks, which is another part of quantum physics. But then, so there are 3 quarks. Now, although in the early universe, pressure was so immense that it was as dense as a core of a neutron star everywhere you went. So, most quarks that we know today are confined, which means that they are tightly bound together, can't be broken unless enough pressure is added to them. If you add too much pressure, they'll just collapse into a black hole. They'll bend and warp space and time too much, and you'll never be able to get them back due to the information paradox. But now we must measure these particles, and we must know how they behaved in these early universes. So in the early universe, all particles, since because the Higgs field was brand new, in fact it was in its adolescence at this time, particles, they were moving at the speed of light. Some of them may even exceeded it, according to some of the theories. But according to Einstein's theory of relativity, and of course, as you see in the background, E equals mc squared, that cannot be possible, because nothing can exceed the speed of light due to terminal velocity. Yes, on Earth there is a terminal velocity for how fast an object can go before it eventually just escapes the escape velocity of the Earth and will leave it. But even in the universe, it has a terminal velocity, or else it will also leave it. Now this is actually seen in the Large Hadron Collider, as you know it. Now, so some particles, they may exceed out of the Large Hadron Collider due to them exceeding such high speeds that they may exceed to different dimensions itself. But we'll get to that in another video of quantum behavior. So now, after we get past this soup of particles that are deconfined, now we enter the dark ages of the quantum world. Now this is when particles start cooling off. Yes, since the cooler something is, the more stable it gets, due to cold usually being more stable than hot. It's a law of the universe. This means that quarks and gluons slowly start patching up together, such as fibers. It's quite amazing when you think about it, on how they may work. Now, the Dark Ages lasted for a few million years before light was brought back to the Earth. There were little pockets of gas that began to cool. These little pockets of gas condensed and become the stars, as we know it. These early stars were very dense. They were dense, hot, young, blue stars. Some were even red, but most of them were blue at this time. These hot blue stars had no planets around them, due to there only being 3 elements created in the Big Bang. There was hydrogen, helium, and lithium. So now, as we get on to the age of starlight, we now start to get seeing a little bit more light in the universe. Now, most of these stars still have little pockets of luminosity around them left over from the early expanding universe. In fact, most of them may even look like a plasma ball that just so happen to have in the background. Now, due to these early clouds were most condensed of hydrogen and helium ions, which patched up together and then condensed, turning into starlights. On the insides of these giant behemoths of stars, they fused other elements together. They fused and fused as we climb up to the periodic table. Hydrogen to helium. Then helium turned to carbon. Carbon turned to nickel. Nickel turned to neon, and neon to silicon, and silicon to iron, and then death. As we know it, though, stars, they explode after this point due to iron cannot be fused and is an unstable element when it comes to this. The iron cores are crushed as the entire weight of the star around it crushes it into a small ball of atomic matter. Then, what happens next is beautiful. And scary, if you were in this type of event, of course. Particles like the electrons and the nucleus that they surround, now they are kept apart from one another due to the weak force. The weak force that is produced by weak gauge bosons and even the Higgs bosons, due to them producing weak outer force, but due to their sheer numbers of them, they can produce stronger force, even a strong force. Strong force is more like gluons, which connect the quarks together, but they're not infinitely strong, but they are pretty strong. But since because of the immense pressure of the star, the strong force overcomes it, and then fuses the electrons and turns into neutrons. All nothing inside atoms turns into something that is completely unstable. So as I have explained a little bit earlier, there are quarks that are inside of the protons and neutrons of atoms. But since because of the electrons that are being fused into the neutrons of them, well, they are adding more mass to the quarks. So some of the quarks may turn into heavy and heavier quarks. Like, for instance, some of them may turn into strong quarks. Some may even turn into strange quarks, which we'll get onto in yet another video from now. So then, what happens next is that since because of all this huge cascade of electrons fusing into the atomic nuclei of atoms, then they get squeezed together, as seen in atomic nuclei. They basically push back with as much weak force as they can possibly hurl against strong force. If gravity wins, and along with a strong force, it'll turn into a black hole, an infinitely dense object which will warp space and time to an infinite amount of mass, almost as if it's like a puncture into the space-time plane. Either that, or if the particles do win, they'll turn into a neutron star, an equally as crazy object, which is ultimately a giant atomic nucleus the size of a city, but yet has the mass of our sun. What then remains is a supernova explosion. Some of the most beautiful events you could ever experience in the entire universe. It'd be a beautiful sight to view. As matter flows throughout the universe, it condenses together yet again, creating a new generation of more stable stars. So there'll also be another law of the universe, which is everything in the universe wants to be more stable than all the other things. That's the problem with strange matter, is that it's infinitely stable. It's the most stable type of matter you can possibly get in the entire universe. And it only exists in one place: the cores of pulsars. So then as these new clouds of gas condense, they create the next generation of stars, and then our sun comes. 4.8 billion years ago, when the sun was created, out of a cloud of gas that exploded from a behemoth. Around the sun were now new elements, heavier elements if you will, such as uranium, there was rhonium, there was even a little bit of plutonium, but it radiated pretty fast. But most of the radioactive elements that were found inside of it were thorium, which exists for 14 billion years, longer than the Earth has even existed, and longer than thorium has even existed. But then there also were non-radioactive heavy elements, like iron, nickel, gold, platinum, palladium, rubidium, osmium, and there also was lead, and there also was mercury. Then these heavier elements created the planets alike. In the earlier solar system, there could have been as much as 30 exoplanets that surrounded it. These planets got dangerously close to each other's orbits and collide together, creating bigger planets. Most of the planets, as we know it, collided into bigger gas giants, which are planets so dense that they can no longer hold a solid surface. Now, third planet from the Sun, the Earth was formed. A hot, burning ball of magma. It would have looked much, much different than what we have known today. Although in this early Earth, there was no moon around it. In fact, lots of planets didn't have moons around them. In fact, most of the moons that are around Jupiter and Saturn, which are the planets that have the most moons, of course, they were mostly rogue planets that were captured by these and were pulled away by tidal forces, creating rings. The Sun has 5 rings, while Saturn has 500 rings. But now, speaking of rogue planets, that is how our moon was created. Although it wasn't created by a rogue planet, like it wasn't just captured by the Earth. Yes, the rogue planet basically just a sad, lowly ice planet that was captured by a star, giving it warmth and light as we know it. But then, what happened to the Earth in the end? There was a rogue planet named Enterthea that collided with it. A little over 3 billion years ago, when the Earth was starting to cool down, and the planet started getting into stable Kepler orbits. But the Earth had one final blow waiting for it when Enterthea collided with it. It didn't collide head-on, but more like a splash. More like that, instead of smacking together. Although some physicists are actually starting to proclaim that, yes, it did collide head-on, and creating a synestia, which is sort of like a donut-shaped object, which brings in moisture to the inside of it, while creating little exoplanets around it. It looks almost as if it's like a red velvet donut, if you will. A celestial donut. Anyways, but most people believe in the giant impact theory instead of synestia hypothesis. And due to the synestia hypothesis is in the scale of theorizing, it's quite new, if you will. But it is definitely a promising theory. But most of them still believe in the giant impact theory, which collided strongly with the Earth, creating rings around it for a little bit over a few centuries. The Moon was formed. A fast rotating, tightly locked, small piece of magma hurtling around another bright piece of magma. As they both cooled down, they started to look a little bit more like as we see them today. The Earth, it created life a little bit over 1 billion years later. It's quite amazing when you think about it, on our story of the universe. And then everyone knows what happens next. Like, for instance, there was the rising oceans that were arriving due to the elements that were creating new ones. Water was solidifying, creating deoxyribonucleic acid. Then that created cell walls due to glucose molecules that were arriving. And then these cells, they condensed together, creating multicellular beings. These multicellular beings then became land animals alike. Until all of this eventually came to mammals, and advanced beings began. These advanced organisms roamed throughout the land as we know it. These organisms, they soon began passing down genes instead of just replicating on their own, creating mutations throughout the universe, and bringing more diverse life as we know it. Some species began breeding with other species that were unknown to their kind. Others stayed with themselves and died out. All of this then became you, dear viewer. You are 3.8 billion years of evolution. Became you. Over all that time, over all the space, over all this noise is going off in the background, of the sound waves that are traveling through the air from my vocal cords. They're bouncing off of the walls of my room. You are a pile of elements that is alive only for a moment in the universe, and then blows out like a candle, spreading its genes yet once more over natural selection. It is said that, as Carl Sagan has said, it is said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration on the folly of human conceits. That is how the universe was created. That's how we became to know ourselves. But that's only as we know it. We don't know exactly how it was created. We only know a split section. Our theory of the Big Bang is like reading a book, but only halfway reading it. We only have half of the information done in this wild, beautiful, and prosperous universe. Thank you all for watching this episode of Universum.